You stand in front of your microwave watching a bowl of soup spin slowly behind the glass. Steam fogs the inside. The light is on. Through that little metal grid on the door, you can see the food cooking from the inside out somehow, and your face is maybe 6 inches away from it. So here's the question nobody really stops to ask. If that machine is filled with the same kind of energy that radar uses to detect aircraft from 50 miles away, why isn't it cooking your eyeballs through the window? Why doesn't it leak? Why is there a tiny black grid pattern on the glass? And how is it that opening the door for half a second doesn't blast a wave of radiation across your kitchen? The answer isn't a thick lead shield or some expensive insulation. It's a piece of physics so elegant it almost feels like cheating. And it's been protecting you from your own appliance every single day since 1967. Here's the part most people get wrong right out of the gate. They think the metal mesh on the door is some kind of filter, like a coffee filter. Holes too small for the dangerous stuff to pass through, holes big enough to let the light through so you can see your food. That's the assumption. It just happens to be wrong. The mesh isn't filtering anything. It's doing something much weirder than that. Microwaves inside your oven aren't tiny particles. They're waves. Specifically, they're radio waves operating at 2.45 gigahertz. That sounds technical. It just means they vibrate 2.45 billion times per second. And every wave has a wavelength, the distance between one peak and the next. For your microwave, that distance is about 12 centimeters, roughly the length of your hand from wrist to fingertips. Now look at the holes in that mesh on the door. Each one is about 1 to 2 millimeters across, so the wavelength of the radiation trying to escape is more than 100 times bigger than the holes. It's trying to escape through. Quick favor before we get to the rule that changes everything. If you've ever wondered about the engineering hiding in the everyday objects around your house, hit that subscribe button. We dig into the science behind the things you use without thinking. Now back to the microwave. Here's the rule. When a wave hits a hole that's much smaller than its own wavelength, the wave can't pass through. It just bounces back. Not most of it, not 99% of it, effectively all of it. The hole isn't a filter. It might as well be a solid wall as far as the wave is concerned. Visible light, the kind that lets you see your food, has a wavelength of about 500 nanometers. That's 500 millionths of a meter. Compared to the 1 millimeter holes in the mesh, visible light sees those holes as enormous, like throwing a tennis ball through a barn door. So light passes right through. You see your popcorn bag inflating. The microwaves stay trapped inside. Two completely different forms of energy. Same metal grid, same holes, two completely different outcomes. Because wavelength is everything. This whole setup has a name. It's called a Faraday cage. The principle was demonstrated by Michael Faraday in 1836. He built a large, room-sized enclosure lined with metal foil and showed that no matter how much electric charge he applied to the outside, instruments inside the cage detected nothing. The charge stayed on the surface. The interior was untouched. Your microwave is a Faraday cage with a window. That's it. That's the entire trick. But the mesh isn't the only thing keeping you safe. Open your microwave door right now and look at the edges. Run your finger along the inside frame. You'll notice the door doesn't actually press flat against the body of the oven. There's a small lip, a channel, sometimes a strip of dark plastic running around the edge. That's called a choke seal. And it's the second line of defense. Even when the door looks closed, there's still a microscopic gap where the door meets the frame. A wave that long, 12 centimeters, could in theory try to squeeze out through that thin edge. The choke seal is engineered to be exactly 1/4 of the wavelength deep, about 3 centimeters. When a microwave tries to escape through the gap, it bounces inside that channel and comes back out exactly out of phase with the next wave behind it. The two waves cancel each other out. Destructive interference. The radiation is essentially erased at the door seam. Then there's the third line of defense, the interlock switches. There are typically 3 of them, hidden inside the latch mechanism. The moment you crack the door open even 1 millimeter, the switches cut power to the magnetron. The component inside that actually generates the microwaves. Power dies almost instantly, faster than the door can physically open wide enough for your hand to reach inside. By the time anything could be exposed, the radiation generator has been dead for thousands of times. longer than the human reflex window. 3 independent systems: the mesh, the choke seal, the interlocks. Any one of them alone would keep you safe. All 3 together is overkill on purpose, because the consequences of failure aren't theoretical, they're FDA regulated. Here's where most people are surprised. The Food and Drug Administration sets a hard legal limit on microwave leakage. Under federal regulation 21 CFR 1030.10, no oven sold in the United States can leak more than 5 milliwatts per square centimeter measured 5 centimeters from the surface over the entire lifetime of the appliance. That sounds technical. The simple version is this: the legal limit is set far below the level that would cause any measurable harm to human tissue. And in practice, most working microwaves leak far less than even that legal limit. So when your oven is brand new, it's leaking far less than the limit. When it's 10 years old, still far less. When it's 20 years old with food crusted in the door seal, it might be leaking slightly more than when it was new, but still nowhere near a level that matters. Now here's the history almost nobody knows. The microwave oven wasn't invented in a kitchen. It wasn't invented to cook food. It was a complete accident. In 1945, a Raytheon engineer named Percy Spencer was standing next to an active radar magnetron, the kind of equipment that powers military radar systems, when he noticed the chocolate bar in his pocket had melted into a sticky mess. Most people would have shrugged and bought a new candy bar. Percy got curious. He sent someone to fetch popcorn kernels. They popped. He tried an egg. It exploded. Within a year, Raytheon had filed the patent. By 1947, they were selling the Radarange, the first commercial microwave oven. It was nearly 6 feet tall. It weighed close to 750 pounds. It needed plumbing for water cooling. It cost around $5,000 in 1947 money, roughly $70,000 today. Restaurants bought them. Almost nobody else. The first countertop home model didn't show up until 1967, made by Amana, a division of Raytheon. It cost $495, still expensive, but no longer absurd. By 1986, about 25% of American homes had one. By 1997, the U.S. Bureau of Labor Statistics reported that figure had climbed past 90%, and the entire safety architecture, the mesh, the choke seal, the interlocks, was largely worked out before that 1967 model ever hit the showroom floor. Here's the part that should genuinely surprise you. You've been living surrounded by this same physics your whole life without ever noticing. That MRI machine at the hospital, the whole room is a Faraday cage. The walls are lined with copper mesh to keep outside radio signals from interfering with the scan. Same principle as your microwave door, scaled up to room size. Your car. When lightning strikes a moving car, the people inside are usually unhurt. Not because of the rubber tires, that's a myth. It's because the metal body of the car acts as a Faraday cage and routes the electricity around the passenger compartment. The little gray sleeve your new credit card came in, that's a Faraday bag. Mesh woven into the fabric to block radio frequency scanners. The shielding around the cables behind your TV, braided metal mesh, blocks interference. Same principle. The fence around an electrical substation, grounded mesh, same principle. The walls of a recording studio, lined to block dio interference from leaking in and ruining the take. Every single one of those objects is using the exact same trick your microwave uses. Wavelength versus hole size. Picked correctly, the metal becomes invisible to one kind of energy and a perfect wall to another. Now for the honest trade-off. Microwaves aren't completely risk-free. If you damage the door, bend the frame, let food crust into the seal for years without cleaning, or run the oven with the door visibly warped, leakage can creep up. The cheap radiation detector you can buy online for $30 probably won't measure it accurately. Those consumer testers are notoriously unreliable. If you genuinely suspect your microwave is leaking, the answer isn't to test it, it's to replace it. A new countertop microwave costs less than $100. The repair is almost never worth it. The other honest concern, the old warning about pacemakers and microwaves, was mostly relevant in the 1970s, when both technologies were less shielded than they are today. Modern pacemakers have built-in shielding. Modern microwaves leak negligibly. The two coexist in millions of homes without issue. But if you have a pacemaker and you're worried, the answer is the same as everything else. stand a few feet back. The intensity of any leakage drops sharply with distance. A few feet away is essentially nothing. So here's where you land. That little metal grid on your microwave door isn't a filter, it's a wall. The choke seal around the edge is a wave canceller. The latch isn't just a latch, it's a triple redundant kill switch. The whole appliance is a Faraday cage your great-great-grandfather's physics professor would have recognized instantly, wrapped in 21st century convenience. You've been standing safely 6 inches from a 1,000-watt radar transmitter every time you reheated leftovers, and you never had to think about it once. That's not luck. That's nearly 200 years of physics, 80 years of engineering, and 3 independent safety systems all doing their job quietly while you wait for the popcorn to finish. If you think microwave ovens are weirder than they look, wait until we get into why the inside of your oven has a spinning glass plate. Because the reason isn't to cook the food evenly, it's to fix a flaw in the physics that engineers couldn't solve any other way.